Okay, welcome to the next segment of lectures on muscle damage. It's actually a real exciting topic and has a lot of implications to how you program your training, what the consequences of those programming choices are, and how you're going to need to rest. First question is, what is muscle damage itself? Well, muscle damage is essentially disturbance of the muscle fiber cross-striated band pattern. So you can see here and the Z line up in the actual first part of this picture completely intact. If you have minor damage, you'll have disruption in that Z line. However, in extreme conditions, the Z line can be destroyed, as you can see at the bottom of this picture. Now, it's not to say you have damage, but there are a number of symptoms that come along with that. The first is you have a loss of strength. And you have other symptoms such as inflammation, edema or swelling, and an increase in proteins from the muscle that leak out into the blood. You're also stiff, and you obviously have things like DOMS or delayed onset muscle soreness. So this is a really good depiction here. We're looking at muscle, control muscle there. You see clear alignment of the Z lines. Here we have moderate damage. The Z lines are essentially streaming here or zigzagging. Here we have extreme damage, complete disarray of the fiber, and here we really have destruction of the sarcomere itself, in which that sarcomere will likely be lost. In this sort of a overview, we have normal sarcomeres, fallen eccentric contractions. You have overstretched sarcomeres. If you go beyond that, they're just disrupted but can be repaired. When we actually start getting membrane damage, there are certain issues such as problems in cell signaling and falls in tension, but this can be recovered. However, the last part is you can actually have destruction of the sarcomere itself, and that cannot be recovered from. So what actually occurs? How does the sarcomere get destroyed? Well, if you look at this graph here, in the upper portion, when this individual is lifting on the concentric phase or on the way down, we see that the structural or cytoskeletal component of the fiber itself is taking force, but part of that force is also carried on the cross bridges themselves. However, when the muscle fiber is overstretched, now essentially what's happening is you lose some of the cross bridge formation, and a lot of the tension is purely borne by the cytoskeletal proteins. So again, on the descending portion, more tension is borne by the passive cytoskeletal proteins, and the sarcomere may be damaged beyond repair. So oftentimes if you look under a microscope, you'll look at the Z lines and you'll see they start to widen or sort of smear. And this may indicate a couple of things. It could indicate a loss of cytoskeletal proteins from damage, or it can indicate a loss of proteins because they're being remodeled. It's also a possible depiction of a popped sarcomere. Popped sarcomere is what we call destroyed sarcomere. So if you lose sarcomeres because they're destroyed, is there evidence for that? Well, there actually is evidence for that. What you're looking at here is elbow flexor volume. And if you look at bout 1 at elbow flexor volume in these untrained subjects, they have a vigorous, high-intensity eccentric bout of training. We know that the volume goes down, and after 56 days, that volume stays suppressed. Right? So the main point is initially you have a swelling response, which you say day 0. Once the edema leaves, you actually see a decrement in volume of the elbow flexors, And this would be indicative that you're actually losing tissue, possibly at the sarcomere level. This is sort of what it looks like here. Basically, if you think of a chain, the weakest link in the chain is what's going to be destroyed. So those weak links are likely stretched, or weak sarcomeres are likely stretched beyond the point of the cross bridges being able to bear the load, and those are popped or destroyed. So now the weak sarcomeres are lost. However, after a period of time of continuing to train, you may recover that volume by adding additional sarcomeres. If you look under a microscope, we can see here what the depiction of additional sarcomeres, or sarcomerogenesis, and that's the addition of sarcomeres here. That's depicted by double Z lines. So let's talk about skeletal muscle remodeling. So one of the things to understand is, again, if we look here, if you look at pre-eccentric and training bouts, you see that's force. You see force goes down immediately post and doesn't return until about 160 hours after the bout. Part of this may be due to remodeling responses happening in muscle. So look at the muscle in graph A and graph B. What do you notice? You notice that there's some absence of certain proteins in graph B. Well, those proteins that you're looking at are called desmin. And desmin essentially is associated with the Z lines, and it helps to hold adjacent sarcomeres together. So desmin's a cytoskeletal protein. If you look, what graph C is, the number of desmin negative fibers. What that means is this: basically the number of fibers that have losses of desmin, okay, in them. So as this goes up, it means you're losing more and more desmin. And as you notice, from control to 6 to 12 hours, more and more fibers are losing desmin, and that doesn't come back to baseline until about 72 hours. So a loss of desmin staining indicates that the desmin proteins are either being degraded or remodeled. It's likely a combination of the two. Now, what we're looking at here is the amount of desmin per level of actin. And essentially, if you look here from control desmin to all the way to 168 hours, desmin actually starts to increase. So it may initially go down, but then it actually rebounds and increases. And what this is suggesting is a reinforcement of the sarcomeres to prevent future damaging bouts of exercise. So here's a summary of the stage in muscle damage. We have an eccentric training bout. The fibers overstretched, and you have disrupted sarcomeres, leading to a decrease in force. You have inflammation and degradation of damaged tissue, and that leads to DOMS and stiffness, as well as lower range of motion. Then finally, we have regeneration of damaged tissue, which can lead to hypertrophy, possibly hyperplasia of sarcomeres. Or if you damage beyond repair, that may last, you may not hypertrophy. And this leads us to the understanding of why. What are the consequences of muscle damage? Because as either a practitioner or a research scientist, you can use these markers as an assessment of the extent of muscle damage. So what are the consequences? Well, one is a loss of force. So we look here. After training, this is 0 days after training, immediately after training. You look at isometric contractions and concentric, you see only a small drop in force. Actually, with the isometric, you don't. But with the concentric, you do see a drop of force. And that's likely due to metabolic fatigue. But in a day, you're recovered. However, if we look at the bottom graph here, which is eccentric damage, we see a large, robust drop, like 50% drop. And that doesn't recover until like after a week if you're an untrained individual, right? So suggests that eccentric might lead to more mechanical damage. Why is this the case? Well, if we look here, this is looking at force output and electromyography. An eccentric contraction can generate more force output than a concentric. However, if you compare maximal eccentric versus maximal concentric, you'll notice that the activity in the muscle is around the same. And this is because on an eccentric contraction, a lot of the force is borne by the passive tissues in the cytoskeletal network. So, if you're recruiting less muscle but can generate more force is borne by less muscle fibers, and hence greater skeletal muscle damage. And again, eccentric muscle actions use both active and passive force. Passive force is produced by connective tissue surrounding the muscle tissue, cytoskeletal proteins and tendons, and passive tension may overload cytoskeletal proteins, producing structural damage. So, popping sarcomere length tension changes. Damaged sarcomeres are turned into passive elastic elements instead of contractile elements as before. So, think about it. Normally you have, say, a chain of sarcomeres. If one pops, the optimal filament overlap is going to change between sarcomeres, right? So we know that within a sarcomere you have this optimal filament overlap. But if you have one sarcomere that's simply just stretching and acting as passive tissue, that's going to change the compliance of the system, and you're not going to hit optimal force into essentially a longer range of motion. And you can see that here. If you look at joint torque pre and then joint torque post, we can actually clearly see that the angle to reach maximum filament overlap, which is indicated by force output, post is much larger than pre. And it's likely that's caused by these passive sarcomeres that are no longer functional. Now, is too much damage, well, too much? Well, if you look here, if the initial bout is extreme, greater than 70% strength loss, it could take 30 to even as long as 89 days to recover. And again, this may be due to loss of sarcomeres or chronic inflammation. So you're looking here, you look percent of initial MVC post. This is an extreme muscle damage activity. We see Priscilla Clarkson here as sort of the queen of muscle damage, the late Priscilla Clarkson. That percent initial MVC goes down drastically. So basically, she beat these untrained people up so much that they had a greater than 70% strength loss. All right, that's a serious muscle damaging bout. And after 26 days, it takes them 26 days on average to recover. But if you look at a couple of these subjects, like M3 and M4, subject 3 and 4, they had 80% and 76% declines in force. And if you look, literally 47 days later, even 54 days later, they're still not recovered. You know, actually M4 recovers by about 55, 60 days. And if you go out 75 days later, M3 is still not recovered. So you got to be real careful on how you train your clients. You can't just beat them into the ground. You have to have a logical plan. Other components that we see with damage, this is me back in grad school here, creating muscle damage with with an isokinetic dynamometer. We deal with this individuals. We had them do a maximal eccentric contractions for 55 contractions. Now what happens is soreness goes up. For example, if you look 48 hours, we had 3 groups here. 48 hours soreness was elevated. And what we think is going on is this, along with this, is that serum protein, so proteins actually in the muscle, when you have damage to the muscle, leak out into the muscle. And that's creatine kinase, for example. So creatine kinase in the blood is often taken as a marker of damage. And we can see that here, an increase in creatine kinase in the blood in our study here. It peaks around 48 hours. And also we see lactate dehydrogenase, which is another intramuscular enzyme. Damage can also be looked at by edema, which is measured by change in muscle thickness and limb circumference. It can be measured by stiffness, which is measured by passive tension, as well as decreased range of motion as a result of edema. So let's talk about factors that maximize damage. We have contraction type, we have intensity, we have volume, and we have velocity. So if you look at contraction type, we see maximal eccentric exercise results in more muscle damage, or creatine kinase in this case, than maximal concentric exercise. That's important to sort of pick out. But again, as we talked about in our hypertrophy lectures, maximal eccentric contraction would also have more force because you can lift more maximally eccentrically. So moving to intensity, what we're looking at here is relative stimulation force, which is a factor of intensity, and Z-line disruption. We see a pretty decent relationship, 0.73 relationship between percent maximal voluntary contraction and Z-line disruption. So basically, the higher the intensity plays a role in causing damage. So very low intensity, you'll likely get no damage, or very little. Very high intensity, damage occurs. This is another good example here. We have the light gray group is downhill running, which is a low intensity bout, but it causes muscle damage. And then we have EF, which is eccentric maximal loading, and that's the dark gray. If you look at creatine kinase in the blood, the maximal intensity contraction ended up causing the greatest muscle damage in this case. And as we see here, basically maximal eccentric contraction produces more edema than submaximal 50% contraction. So it is dependent on intensity. But it's also dependent on volume, which is going to be an interaction between intensity and as well as the volume. So if you look at 50% 1RM, these are untrained people, but if you go from basically creatine kinase goes from 213 to 535. But if we look here at 75%, we see it go from 157 to 668. And that is a sweet spot because it's relatively high intensity, but the volume can still be high. And then if you go to 110% intensity, the volume, yes, is low, but the damage is high because intensity is so high. 90% of the 1RM, the intensity is high, but the volume's low, and so you don't get the increase in CK. So either you're going super high, maximal, or you're having a combination of volume and intensity with the moderate, leads to the greatest increases in muscle damage. As far as velocity of contraction is concerned, when there seems to be a volume effect, but when you control for volume, if you look at graph B, what you're looking at is the essentially the drop in maximal voluntary contraction, and you see F210 versus S210, and basically what you're seeing here is S is slow, F is fast, and you see clearly that maximal voluntary contraction lowers more in the open bars, which are F10. Is damage necessary for growth? The damage here, the data here is limited. What I can tell you is if you look at blood flow restriction training, it's clearly not necessary for growth. But tension itself may be a mechanism for growth, and the result of tension is muscle damage. So there's some studies on it, but they're unclear. Now, if we look at velocity of contraction, if you look at the proximal, mid, and distal sites, the fast eccentric contractions, fast training, is producing more hypertrophy than slow training. Whether you're doing it eccentrically or eccentrically in particular. And you also have more damage in fast contractions. So if you go to the right here, you look at fast contractions, more muscle damage. You go over to the left, you look at type 2X fibers, type 2A fiber size, greater muscle fiber size. So if we were to conclude, we would say that damage is a disruption of the muscle fibers, which leads to declines in performance. It's proportional to force velocity as well as contraction type, and must be taken into context when designing your training split. Thank you, and I'll see you for part 2 of this lecture.